for the ensuing semester examinations, which begins on 22nd of May. We plan to continue this lecture every year as we do for the case of Professor Saha Memorial Lecture. Once again, I welcome and thank you all for being here with us. Thank you.
Thank you, sir. Now I would like to call on stage Professor Saibal Gupta, our speaker for today, and the head of the department, Professor Shankar Bose, to offer floral tribute to Professor Shah. Thank you, Professor Bose. I will now introduce today's speaker, Professor Saibal Gupta, to the audience. Professor Gupta is at present an HAG professor in the Department of Geology and Geophysics, Indian Institute of Technology, Kharagpur. He currently also holds the responsibilities of the Associate Dean, Faculty of Sciences at IIT Kharagpur. Professor Gupta earned his bachelor's degree in geology honors from Presidency College, University of Calcutta in 1987. He completed his master's degree from Calcutta University in 1989. Although examinations for the masters in that year were held in May 1990. Subsequently, he spent a year as a CSIR Junior Research Fellow at the University of Calcutta. In October 1991, he left for the United Kingdom with a Cambridge Nehru Fellowship and completed his PhD from Department of Earth Sciences, University of Cambridge, UK in 1995. Returning to India, he joined as a visiting lecturer in the Department of Geology and Geophysics at IIT Kharagpur in August 1995. He has worked at IIT Kharagpur all his professional life, from an assistant professor in 1998, associate professor in 2004, and then professor in 2010. Professor Gupta's research interests include nature and evolution of orogeny with a particular focus on the thermal evolution and composition of the lower crust. He integrates structural, metamorphic, geochemical, and geophysical methods to study crustal behavior during orogeny and its exhumation. His work extends to terrain amalgamation and the construction of supercontinents such as Rodinia and Gondwanaland. He also applies his expertise to geohazard assessment, mineral exploration, also reached beyond Earth through collaborative efforts with the Space Application Center in Ahmedabad, where he investigates terrestrial analogs for Martian surface features. He has published 75 research papers across many renowned peer-reviewed national and international journals like in Journal of Structural Geology, Tectonophysics, Journal of Metamorphic Geology, Journal of Geophysical Research Planets, Journal of Geophysical Research, Solid Earth, Geophysics, Scientific Reports, Natural Hazards, Precambrian Research, Journal of Earth System Science, Icarus, and many more. He has supervised 17 PhD students, many of whom are now researchers in national and international organizations, universities, and institutes. Today, he will be speaking on continents, water, life on Earth and beyond, the geologist's story. Please join me in giving a warm welcome to Professor Saibal Gupta.
I can be heard, I think. So as they are setting this up, it gives me an opportunity to say a few words, which is what I intended to say preceding my talk. It's a great nostalgic feeling for me to be back here. And this particular hall, I remember it more for watching Kurosawa and Satyajit Ray retrospectives rather than anything else. What is really nice to know now and realize is that people can actually understand words when they are sitting in the audience here. Because when I was a student, the acoustics were extremely bad. And now it's significantly better because I could hear people when I was there. Apart from the nostalgia, the sheer nice feeling of being back here, I must actually thank Professor Shankar Ghosh and the Department of Geology of Presidency University, and of course the Geological Institute, of which I also am a member. So all of this, for making this possible, for me to be able to deliver the first lecture in memory of somebody who I think represented to us at that time the Department of Geology, Presidency University. And it was more or less realized all through the country that this was the case. It is okay, so let me just begin from this point. Anyway, I think we're a little overdue. So once again, thank you for having me here to talk on something that is not really related to what I learned when I started off learning here, but it is in a way related, and related to the very gentleman after whom we're all assembled here today. Professor Saha was a person who actually not only did geology, but he also realized the importance of doing geology in such a way that we could reach out to other disciplines, to reach out to the service of mankind. So he actually was always exploring the frontiers of what could be done and what could be done in this particular country. So as a result, I think the only things that we possibly were able to imbibe in some way, at least I have been able to imbibe in some way, is trying to explore the frontiers of what I could do with whatever little I knew about the subject. And whatever I have done so far, in fact, dealing with planets, planets and planetary bodies outside the Earth, is something that I never thought of doing, that never thought that I would be able to do when I started off doing geology. So today, I'll be talking about a few things that I have done together with my students and a very useful and efficient group of collaborators who have taught me a lot over the years. So I'll be talking about continents, water, life. Now, these are three very important ingredients to our existence. We survive as life because we have continents and water. Exactly how this happens, water is fairly obvious. Continents are not that obvious, but we will be going into what exactly it means, and even what the formation of life means. And when I end, I hope to tell you how that it makes us realize how lucky we are, really, that where a number of factors luckily came together to enable us to exist. Now, if we begin right from the start of where it was here, Professor Saha, this is not how I remember him, by the way. I graduated in I joined this department in 1984, and when the department, he retired officially the next year, continuing as an emeritus professor, but he was no longer head of department. But one of the things that we realized Professor Saha was very fond of was this thing to the right. So those of you who may not know Professor Saha would actually know this image to the right. And this is one of the areas in which he spent much of his life working in. This is a map of the Singhbhum plateau, something that he was fascinated with, a fascination which we could understand as students had something to do with examinations which would appear every alternate year. There used to be a question on Singhbhum every alternate year. And then in that particular context, we were forced to study it, and we didn't like it when we did. And we really wondered, what made Professor Saha so fascinated with Singhbhum? Well, now, at the end, let us say, of my own academic life, I now realize that there's a lot going for it. There are reasons why he found this so fascinating. Now, this little bit of Singhbhum, it's a part of the Indian Earth's continental crust, which is among the oldest bits of the continental crust we know of in India. Not just that, it is also significantly preserving several bits of Earth history which are actually not yet documented elsewhere on Earth. And that really has to do with, let's say, the emergence of continents, something that has been done with Singhbhum very recently. Now, in this region, if you look at this particular map, you see a lot of rocks actually marked on here. One of the units that is very prominent is this particular one here. This is the one which gave us a lot of, what should I say, a lot of sleepless nights when I was students. This is the Singhbhum granite. There were apparently 12 phases of it, and 12 types of granite, which were erupted in 3 phases. I don't still remember exactly what they were, why they were there. But I do realize now that it actually is a significant part of the Earth's crust that we look at. You have granites of various sorts which actually stabilize the continental crust elsewhere on Earth as well, not just in Chile. So there was a reason why he was interested, because this was one of the earliest parts that you could see. And it was telling us bits about Earth history, which we are not able to really see. We can't go back in time. So all that we can tell about what happened in the past is by looking at these rocks. So what really is fascinating is this is the way in which you can actually begin to work out how continents were formed. And why is that important? Because if you look at any map of the Earth, so you will see that it's a distribution of continents as well as oceans. Now in this, you see that you have the green areas which represent the continents, you have the blue areas which represent the oceans. Now essentially the Earth's surface is dichotomous, crust-wise. So we have 2 types of crust. One is the type of crust that dominates what we see in the green areas, the continents, and the other part is the part that lies below the blue waters that we see here, and that is basalt, which makes up most of the oceanic crust. So we have completely different types of crust on Earth, so it's essentially a dichotomy. Now, this dichotomy is not just apparent on a map. There are reasons why they are different, because continents and oceans themselves are fundamentally different entities. Now, if you look at continents, the reason why we realize that they are different from the oceans is, first of all, they're more elevated than the oceans. We have a mean sea level, and above that, right, we have the continents on which we live. So we are able to live on continents, and we can look and enjoy the seashore. But then what lies below the sea is also rock, and that rock is very different from the continent on which we live. Now, continents themselves, on an average, have a composition which is that of a rock called a granodiorite. Now, these are silicic rocks. Now, by silicic, throughout this talk, I'll be referring to those rocks which have a silica weight percent of over 65. So you have more than 65, more than 2/3 of the rock is dominated by silicon dioxide. So continents are largely made up of one type of rock, which is silicic, which is called the granodiorite. On the other hand, if you look at the oceanic crust, it's made up of different rock. This rock is a basalt, and this basalt contains significantly lower quantities of silica than the continents, about to 55% of silica. Now, we know that continental crust is also less dense than the oceanic crust, and that really is a consequence of the amount of silica it has. Because continental crust contains more silica, and silica is a lighter component, therefore, overall, the basalt, which contains less silica, is heavier. So there is a density contrast between the continental and oceanic crust. Now, in addition to that, we also know that the continents are bigger than the oceans. So the continental crust on an average is old. Whereas if you look at the oceanic crust is only around, the oldest part of it is only about 200 million years. So there is a drastic difference in ages between the two, and that we know happens to be because of the phenomenon called plate tectonics, which actually consumes oceanic crust repeatedly over time, and it cannot do the same with continental crust. Now, why are these continents so important? Now, in the past, we knew there were continents and there were oceans, but for a long time, we never really realized why they were so important. Now, continents, we realize that sometime in the geologic past has emerged from below sea level to above sea level. And this emergence from below sea level, this has been responsible in a very significant way of controlling the surface temperature of the Earth. Now, the surface temperature of the Earth, it varies from place to place on the surface, but overall it has maintained an average value that can actually sustain liquid water on its surface, and that has happened at least from 4 billion years. As far as the rock records can tell us, we have sedimentary rocks which were deposited underwater from 4 billion years. And that means that we must have had liquid water for 4 billion years, and we still have liquid water on the Earth's surface today. So the surface temperature must have been roughly within that, give or take variations in the atmospheric pressure. Now, the emergence of the continents from the oceans themselves, apart from controlling the surface temperature, acting as a natural thermostat, in other words, it was also responsible for increasing the amount of oxygen that is there in the atmosphere. This was indirect, but nevertheless, this was responsible. The emergence was what was responsible for what followed. The two great oxidation events, one at 2.4 billion years and one at about 800 million years. So both of these are linked to the emergence of continental crust from below the oceans. So the continents are actually very, very significant, not just for maintaining surface temperature, but ultimately, in some ways also, for sustaining life. Now, the question then comes, how do we make continents? If we look at the Earth, right, and try to look at how continents are created, we first have to once again realize what they are. Most continents are made of silica-rich rocks, and these contain over 65% silica. Now that's one of the fundamental things that's of importance in making a continent. Now on rocky planets, those which contain silicate interiors, you have a silicate mantle, which is roughly of the composition of a particular type of meteorite called a chondrite. And this type of rock, right, dominates this chemical composition dominates the Earth's mantle, and when it melts, the Earth's mantle melts, it produces a liquid which has the composition of a basalt. Now, the mantle has a little less than that, it's around 40%. Now, we normally assume that silicic rocks, which contains more than 65% silica, these are produced by a process called fractional crystallization of a basaltic magma. Now, a basalt liquid is produced by melting the mantle. And what we are doing then is crystallizing things from the basalt magma, which contain less silica than the basalt. As a consequence, the composition of the magma progressively becomes more silica-rich and ultimately becomes silica-rich enough to form and stabilize a continent. Now, to do this, we now realize that a basalt or basaltic magmas cannot fractionate to generate a granite. You need to have a certain amount of water inside that basalt for Bowden's reaction series, as many of us know, to operate. If you don't have water, you cannot actually fractionate a basalt to give a granite. As simple as that. Now, this is therefore one of the best ways to make a granite. But there are other ways, and responsible for producing continental material today. These may not have operated in the past. So therefore, we need to actually understand, right, how the first little bit of continental crust must have formed on Earth. But the problem is the Earth's surface is so very dynamic, is that weathering and erosion over ages has really degraded the earliest continental crust. So we can see evidence for it, but we may not actually be seeing the oldest bit of continent that was produced on Earth. So where do we see this? Because on a dynamic planet, it's never going to be possible to see that. So we can actually look for silicic rocks on other planetary bodies. Because we know that these other planetary bodies, for example, the Moon, Mars, Venus, these are rocky, and we know that they contain the capability to actually produce silicic rocks. It's important for us to see if we can find any evidence of granites being produced on these planets. Maybe that will be preserved there, because that was frozen in time. Now, are there silicic rocks on other planets? Now, if we look at the planets, then it's only the Moon is the only one on which we have physically landed as humans. Mars has had rovers on it. Venus has just had one random mission. But whatever little information we have tells us that planets such as Mars, Venus, and Mercury, the surfaces are dominantly composed of basalts. This much we know. And there are very rare silicic rocks. They're rare because we suspect that there could be a few silicic rocks, but we're not certain. There are reports, but again, unless you can actually have more definitive proof, more convergence of evidence, you can never prove that there were silicic rocks there. So the most accessible rock, if you're going to look outside the Earth, search for silicic rocks, the best place to look at is the place which is most accessible to us outside the Earth, the Moon. Now, this idea, not for looking particularly for granites, that man could go to the Moon, first originated, I think, but people have been thinking about it, but somebody to put pen to paper and write about it was revered. And this is from a very old book. This is, I think, the cover of the very first edition that was produced. So we think this idea that it was possible to go to the Moon to actually find things out stems from a lot of things that this person told. Now, oops. What's happening here? But this is worrying. There were two images here. Now, for some reason, those images are not visible. So one is the near side of the Moon. I mean, this was the part that we can actually see. One is the far side. There are no images actually missing afterwards, because this is going to be a problem if the images can't be seen. So there is a near side and there is a far side. Now, I just want to mention what this means. It means that when we are looking at the Earth's, at the Moon, we are only able to see one face of the Moon. Because of the Earth's gravity, the Moon's surface is actually tidally locked. And so we can't actually see the whole of the Moon. We can only see one side. That side is called the near side. The part that is away from the Earth is always away. We've never actually seen that physically unless we send crafts to the other side to photograph it, as we have. That is called the far side of the Moon. So we have two different sides. So we are able to see one side which contains a lot of craters and the other side which is the far side. The Moon's surface, however, is not made up of basalts dominantly. It is made up of a rock called an anthracite that actually dominates. It's not the only rock type there, but there are some other types of rocks which make up the surface of the moon. But this is one of the ones that is important. Within some of the craters that you see on the moon, you have patches, dark patches, which you can see on the moon even if you look at it at night. These dark patches are basalts, and these have been erupted into craters that were formed on the moon's surface by meteoritic impact. So, how then do we begin to look for silicic rocks on the moon without getting samples of these rocks? Now, the first thing that we need to worry about is that, is it worth looking for it? Is there any chance that we might find silicic rocks on the moon? Well, one of the advantages we have or the moon has over other planetary bodies is that we have some return samples. And these were primarily from the Apollo missions. So Apollo 11, Apollo 12, Apollo 14, Apollo 15, Apollo 17, all brought back samples. And indeed, all of them brought back samples that had some traces of the presence of evolved lithologies of silicic rocks. Now, most of these return samples, anyway, the samples that you see of the basalts are either clasts or the breccias. Among the silicic rocks that you can see, you have both crystalline varieties with quartz and feldspar, and you also have glassy material, which tells you that there were silica-rich liquids present. Interestingly, in these rocks, which are mostly granophiles, there are no hydrous minerals at all, no evidence of any water being present inside those primitive areas. There are a few samples, very, very small, in which you actually can see graphitic integrals, granophoric integrals between. And there is evidence of a phenomenon that you can see in these rocks called silicate liquid immiscibility. It means that when you fractionate a basaltic magma without water, you can actually wander into silica-rich domains where the magma itself splits into two. One composition which is around 50% weight percent silica, and the other part which contains over 98%. So you can get very silica-rich magmas by this particular phenomenon called silicate liquid immiscibility. And there is some evidence for this in the lunar samples we've seen. But are they silica? These are very small samples. Are they silica-rich constructs on them? Mountains of silica, as we will see in a minute. That's what would really count. And this evidence we have to get from spectroscopy. None of the Apollos have actually landed on a silicic construct. Now, if you look at the surface of the moon, there are red spots there. And these red spots are important because silica-rich rocks have a higher albedo, so the reflectivity is better, the reflectance is better, which becomes concentrated in liquids every time they form. So whenever you melt a rock, some elements actually trace elements prefer to go into the liquid itself because they cannot be easily accommodated into the crystalline structure of the minerals present. So, as a consequence, thorium itself, when it's there, it would tend to be present in more evolved lithologies, and that really is what we are seeing coinciding with the hotspots here. And then there is this spectroscopic feature called the Christensen feature, and you actually see this in the emissivity spectra. Now, the emissivity spectra